Okay, so today we're still going to go into design of transmission shaft, and once we finish, we go to design of beams. Okay, so this is how a typical element will look like when it's under when it's on a transmission shaft. As I mentioned before, transmission shaft is usually specified, designed by mechanical engineers because we are more involved that on things that are in motion, okay, rather than any other discipline. So from here, we realize that stress in the x direction, the normal stress is due to px over a plus by mz over y, izz plus by my over iyz. Now, this is a very typical uh, normal stress. So as you can see, this is probably you guys can recognize this. So this is under eccentric. So the eccentric is due to the px over a. Okay, the eccentric is due to the px over a, and then unsymmetrical. Bending. Okay, so this will give us your stress x, and then the shear for a shaft. Okay, now all these are taken from the notes written last week, so you will have them. Okay, so I've just cut and paste what we have done last week. Okay, so it's just a quick recap before I proceed. So on the shaft, again, this is this. I think I better write this down. This is when we are designing transmission shaft. Okay, and then the shear, right, is equal to T in the x direction, C divided by J. And this is induced due to the torque. The shear is induced due to the torque. Okay. So when due to the torque, what we realize that the shear is maximum at the maximum radius. Okay, maximum radius. And in the design of a transmission shaft, I'm going to highlight all this. Okay. So this is what is not written on the previous notes. And the shear stress induced by the shear force is neglected or is ignored in transmission shaft okay, due to small amplitude. So the stresses induced due to the shear force is small when compared to the shearing stress induced by the torque and relative to the normal stress. So we drop it. Okay. Then given an element like this, we did an example, right? We did an example where we design our, we construct our mole circle over here. So down here, we construct mole circle, right? So our mole circle has both normal stress and shear stress. Okay, so our mole circle has both normal stress and shear stress. And the normal stress is calculated by stress x plus by stress z divided by 2, right? And we know, looking at the element now, okay, looking at element, we realize that stress Z is equal to 0. So we have equation relating stress X divided by 2. And because stress X over here is induced due to bending, okay, due to due to bending. When I say due to bending down here, okay, if you see the previous equation that we've written down here, this is due to bending, and it can be eccentric unsymmetrical bending, one of the most extreme cases where you have normal stress and you also have shearing stress, right? So you also have an axial component, okay? The eccentric is equal to px over a, and then you have your bending moment in both direction, okay? So for our case, stress Z is equal to 0. Then we found that due to bending, right, we let stress X is equal to stress M. So stress M, we call it stresses induced by the bending moment. Okay. Now, the next thing that we want to identify, okay, so what we're trying to do down here is to find our stress average. So given the stress average, so this is not very clear. So the distance from here to here, right? This is your stress average. And then we will find the radius of the circle, which is the average stress plus by the shear in xy component squared, right? So the next question that we ask, so this is how we found our maximum shear, and the maximum shear is equal to the radius of the circle. So like what I've drawn down here, this is the radius of the circle. So why is it so critical to find tau max? Okay. So last week I explained that, hey, if we do a uni-axial tensile test, right? So this is uni-axial tensile test, and we have a value of 600 megapascal. And if we take the element from here, we plot it out on our, we draw an element over here, like what I've highlighted now, we will get a mole circle. Okay, so the mole circle look like this. We assume or we measured. Okay, so this is a measured value that this is equal to 600 megapascal. So then we construct a mole circle, right? And from the mole circle, we realize that tau max is equal to what? 300 megapascal. Okay, and important thing to take note, this is a material behavior. Okay, so that is the material behavior that we got by doing tests, or you got it from a materials handbook. Okay, so remember we had a material handbook that states, let me see, uh last week, I think it's last week or the week before, there's revision, I think it's the week before, that we have a material handbook data over here. Oh no, this is not material handbook, right? So this is our material handbook data. Okay, so we have tensile in tension, the yield stress in tension, and the shearing stress or the shear in the yield shear stress. Okay, so that's where you see the 145 and the 150. So these are all taken in one direction only. Okay, where they're all measured in one direction only. So and if now we go back to our lecture, right? Oops. Go back to our lecture. So from here, right? So this is where you get with the 600 that you see down here, and then the 300 you can get from materials handbook. But how to use this data? Okay, the most important thing is how are we going to use this data? So to use this data, we have to incorporate into our structure mole circle. So this is from our structure analysis. Then we draw a boundary. Okay, so our boundary over here, as you can see, this is our maximum tensile test. Okay, and this is our shear max, and these are material behavior. From here, we draw an operating bracket. Okay, so we draw an operating bracket. So we drew an operating bracket, and you can see all these very dark shaded line. So if the circle happen to be bigger, okay, or the diameter of the circle happen to be bigger, the material will fail. Okay, if the circle is within the space of the shaded region, the material will not fail. Okay, so that's how we incorporate material behavior properties into our mole circle that is constructed based on structure analysis. Okay, then from here you design you specify your shaft under combined loading. Okay, but the property we use is also both under tension or under uniaxial tension or compression or shear. Okay, any questions so far? I know it's a lot to absorb. Don't get me wrong. Okay, I understand that there's a lot to absorb down here. Okay, right. Okay, so from here, I'll explain why Tommix is so important. Okay, so the Tommix value down here, as you can see, like what our example has given, is now become what 300 megapascal. So we need to ensure, right, our structure, the Tommix will not go beyond what 300. Okay, and then we also sometimes, not always, we have to also check that the principal stresses, this point over here, don't go beyond what? Don't go beyond the normal stress location. Okay, right. So let's go further to prove our concept on how to implement Mohs circle now. So we know that tau max, so I'm going to write out this equation now. Okay, so we know that tau max, okay, is equal to, right, we have this, right? So it's equal, so we have tau max is equal to stress average squared plus by shear xz squared. So we know that our stress average, this will be equal to stress induced by bending divided by 2 squared plus by shear stress. Okay, so we know, okay, we know for our case, due to the shaft, okay, we just look at the shaft, the stress M is equal to my over I, okay, and the shear xy or shear xz is equal to TR or TC over J, right? Where C is the maximum radius of the shaft. So I'm going to call this equation number 1. Okay. So we have these two relationship, and we're going to substitute stress M and shear xy into equation, okay, number 1. We're going to put in into equation number 1. So from here, so what you see is tau max will be equal to, right, so M, so sigma M over 2, so this is equal to my over 2I, right, because of stress X divided by 2 or stress M divided by 2 plus by the shear is TC over J. So now you see the relationship with moment and the torque. Okay, so note relative to the shearing stress, note the second polar moment is equal to 2I. Okay, so from here, tau max will be equal to square root of my over J, right, squared, plus by TC over J squared. Okay, then we can remove, and also note that the bending moment at its maximum will occur when this is equal to what? MC over what? MC over I. So when that's the case, you change this to C though, right? So this is also MC over J squared plus by TC over J squared. right? So why this is the case? So if we have a shaft down here, right? And we know that over here, if our moment is acting in this direction, right? So we know that the distance from here